Euclidean geometry, proof of the angle at center theorem. This theorem says the angle which the arc of a circle subtends at the center of the circle is twice the angle subtended by the arc at any point on the remaining part of the circumference. So there's the remaining part of the circumference, there's the arc, and this angle twice that, this angle twice that, this angle twice that. Before we go into the actual proof, let's just go through our thought process. Remember that theorems build on previous theorems and definitions. So what do we know? What do we know at this stage? We have no other circle theorems to build on other than chord theorems. So we know the center of the circle, and therefore we have equal radii. We have isosceles triangles, two isosceles triangle, which means the angles opposite the equal sides are equal to one another. We have exterior angles in triangles, so if I produce that side, there we are, that angle equals that plus that. So if I produce this side, this angle equals that plus that. This angle equals that plus that. And all I've done is transferred that plus that to here, and that plus that to here. But now if we rearrange those, you will see that we have two of that here. So there is the way we're going to go about proving this theorem. Right, into the proof itself. There are two diagrams. We're going to prove it just using the top one first, and then with both. Usually in proofs, you could be asked either of them, so you should know the proof for either of them. They follow exactly the same construction and proof until just near the end, where we've got to part and say add there, subtract here. What is really important though is to make sure that you construct in exactly the same way. So if it says join 2 points here, then you join the same 2 points here. And if you label angles, if you label a particular angle with a 1 and the other side with 2, you must do the same angle here. So let's go into the proof of just the one diagram. Given O center, we have to say that as a given because we cannot show it in the diagram. Required to prove. And remember again, required to prove interprets what's said here into this diagram. Construction. Now, in the previous screens, you'll remember we spoke about exterior angles. So that's what we need. So, and the isosceles triangles. So we need to join PO to give us the isosceles triangle and produce to any point N, doesn't have to be on the circumference, so that we can have the exterior angles. There we are. There's N there. Let's get into the proof now. Notice the labeling. I've just labeled it. It makes life easier than having to use 3 letters, just using P1 instead of BPN, for example. The proof. O1 equals P1 plus B, and that's the exterior angle triangle. Now we argue, but P1 equals B, isosceles triangle radii, and therefore O1 equals twice P1. O1 is twice P1. Now the same thing's going to happen on this side, and as it's exactly the same thing, we can use similarly, but abbreviated to simile. O2 is twice P2. So we have that is twice that, and that is twice that. So AOB, that angle we're trying to prove equal to twice the P, is equal to O1 plus O2, which means it's twice P1 plus twice P2, because O1's equal there, O2's equal there. Common factor of 2 comes out, and P1 plus P2 is the whole angle P, so therefore twice P. And it's proven. AOB equals twice P, AOB equals twice P. Now we'll do it for the two diagrams. Labeled 1 and 2 because I need to refer to them later in the figure. Same required to prove, same construction. Now notice, join PO, produce to N, so therefore I must join PO, produce to N. Now we're going to label the angles in the same way. Now notice that it talks about it here, you can read that, but BON, P1, let's start P1, is BPN. So therefore, I have to say BPN, that whole angle there is P1. So that when we're talking about P1, we know that we're matching in both diagrams. P2 is APN, so therefore here I go APN, so there's P2. O1 is BON, so BON, there's the whole of O1, and O2 is AON, so AON, there's the 2, and they match. Now, what I'm going to do is just look at this diagram and do the proof for most of the way through, so you can ignore that diagram for a while. You can have a look at it and see it does match. Now the same proof as before. O1 equals B1 plus P1 plus B, but P1 equals B, isosceles angle, triangle of radii, therefore O1 is twice P1. Similarly, O2 is twice P2. And there we have it, exactly the same proof. Now this is where we need to separate into the two diagrams, because I'm trying to prove that part is twice that part. And if you have a look at it, it's actually this whole angle less that. This one is adding the 1 and 2 together, but this one here is subtracting the 2 from the 1. Perhaps you'll see why I labeled the one on the right and then the left. Usually we would label the other way around. We're a very left to right society. But I labeled this way around in preparation for this labeling. So we say in 1. And we're going to do exactly the same proof as before. Adding O1 and O2, that equals O1 plus O2, which is therefore twice P1 plus twice P2. Common factor, P1 plus P2, and P1 plus P2 is P. So there, that's finished. Now I go to this triangle here, and I say into AOB is O1 minus O2. Now I'm going to use the O1 and O2 there and substitute. Common factor. And it's P1 minus P2, the whole P1 minus the P2. There we are, which gives me angle P in the original diagram. Now, you probably won't be required to prove this one very often, and very seldom in exams will they give both, because that means they have to allocate a whole lot of extra marks for it when they need to be able to allocate marks for other things. But you could sometimes be hit with this one instead of that one. So do be aware of it.